Alright, let's continue on the sample problem that we're trying to solve. So now we're done with the beam dash 5. We'll now solve for G dash 1. Okay, so solving for G dash 1. Okay, so here's the G dash 1. Okay, so we have the G dash 1, the girder 1 is from this point C, A4 to A2. Okay, and there's a point load coming from this beam right here. So that's a girder. So girder 1. Okay, so let's try to illustrate that in a three-dimensional view. Okay, so here's our, I guess this is balloon number 4, then this is balloon number 3, and balloon number 2. Okay, so we have this B-3, then B-4, B-2. Okay, and we have a wall. So we have a 3-meter wall. Okay, plus we have a slab, of course. Then this is the slab. Then we have a wall. Alright, so the wall would only extend up to balloon 3 only. Okay, so this is just the wall. So there's no wall on this portion. Okay, so since there's let's try to illustrate the loading. So if we have a wall, then meaning it's gonna induce dead loads like this, right? And then since this is a slab, but you notice that the slab is not contributing to this slab is not contributing directly to this girder. Actually, we said that this slab is a one-way slab, meaning that the loadings, this portion of this area transmits its load to this beam dash 3. So, meaning there's no slab. Let's say there's no slab loadings that is transmitted directly to the girder 1. So meaning the load is transmitted from the slab and then to beam dash 3 and then to girder dash 1. So this girder dash 1, if you recall earlier that what I've said, that these are supports. So these are joints or something like the boundary conditions of this beam dash 3. So you can model this like, for example, a simply supported pin roller support, or you can also model it like fixed conditions. So these reactions right here, this joint or support reactions, it will induce a point load on this girder. Okay, so if you try to draw the beam, okay, so we have a length of, this is 2.8, then this one is 2.2 meters, and this point right here is balloon 4, then balloon number 3, then balloon number 2. So the loadings actually is something like this. Okay, so we have a distributed loadings from the wall and then another point load from the beam. So if this is from the beam, then this is already a factored loads, right? So we already have a factored loads right here. Factored loads So that's P dash U. Now what we need to solve is the dead load of this wall. Since it's just dead, then we'll just use this. Okay, so 1.4 dead. We'll use an a load combination of 1.4 dead. So 1.4 times the dead load, which is 0.034, or like something like this. We'll use this value. So we have 0.034 times 3 meters, that's the height. So we can substitute, or we can use this value times 0. kilonewton meter. So we'll use this pen, a thicker pen. So it's good for life. Okay, so where am I? Okay, so this is, if you try to compute this, the values that you'll get is 0.1428 kilonewton per meter. Okay, so that is, okay, so W 0.1428 kilonewton per meter. So with these point loads, so that's coming from B-3. What is B-3? So we have this B-3, we have a 15.4 kilonewton meter. Now if this is a distributed loading, you can actually solve the reactions. Okay, so it's just so this is B-3 and we have 15.4 kilonewton meters. Okay. Now if you try to solve this, this is actually just shear value, which is okay, V, or just equal to R WL all over 2. So you can find this equation from the beam design, or something like beam design tables. Okay, so you can find a lot of loadings and beam conditions in that tables, and the equations for maximum shear, maximum moments and stuff like that. So for this is just simple. So this is the WL all over 2. So the length is 6 meter. The value is just 46 point. Okay, so R is equal to 46.2 kilonewton. Okay, so meaning our loads here is 46.2 kilonewton. Okay, so that's the unit is in kilonewton because it's a concentrated loads. Okay, so now we're done with G-1. So this is already done. Then what's left is the G-B. Right, then let's solve for G-2. If you try to draw this G-2, so let's say this is number 4, then we have value here 3 something, so this 3, then 2 then 1. Okay, so 3, 2, and 1. Okay, so this is it. This is what I'm trying to draw here. So this is 1. Okay, balloon 1, balloon number 2, then balloon number 3, and then 4. Okay, and you notice that this slab right here is not actually contributing directly to the girder, to this girder. Since this is a one-way slab, then the loadings are transferred to beam dash 2, then this one to beam dash 3, and then what's transferred in this girder is the reactions. So at point 3 and then at point 2, there's gonna be point loads here. Okay, so let's write point loads from let's just write point loads from B-3, okay, from B-3, and then this one from B-2. Okay, but on this side right here, on this slab number 1, since this is a two-way slab, then it's actually contributing loadings to the girder. So we have a triangular loading, something like this. But again, you can we try to simplify this and we use the reduced value of Lx over 3 as the tributary width. Right, so Lx over 3. Okay, so that's gonna be the setup. Okay, so how do we get these point loads? So let's say this is PU-1. So PU-1, that's again, if you solve that using the WL all over 2, what you get is 46.2. That's from B-3, and then PU B-2. So you solve again WL over 2, and what you get is 14.97 times 6 divided by 2, that's 44.91 kilonewton. So this one, again, I'll just write it here, B from B-3, and then this one from B-2. Okay, so what is this loadings right here? We already solved that in B-5, right? So we have this value 8.19 kilonewton per meter. Okay, so let's draw the beam diagram and the loadings. Okay, so we have loadings here and then a distributed loadings, then concentrate on those. So this PU-2 is 44.91, this one is 46.2, and this one is 8.19 kilonewton per meter. This one is in kilonewton. Now if you have these loadings, then again you can solve for the maximum shear and then maximum moments. So for now we're done with the beams, and in the next few minutes we'll be discussing the tributary areas for columns. But before that, I'd like to emphasize this, that since we have a lot of let's say papers for the computations, then we can actually tabulate the values in this way. So for example, for the beams and girders, then remember let's say B-1 until G-2, then what's the dead load? Then again, I'm referring to total dead loads. So you can write it down here. Then the live loads, then what's the ultimate, or let's say the factored loads. Okay, so if you have that, then you can solve for the you can tabulate here the Vmax, the maximum shear, and then the maximum. Okay, and in some situations, if we're dealing with fixed conditions, fixed end or fixed supports, indeterminate beams, then probably you can include the negative, or let's say what's the moment in or what's the moment at the support, and what's the moment at the mid span. Okay, so now we'll move on to the columns. Okay, so for the columns, try to draw it here. Okay, so just draw it here, so that's it's going to be clear. So for the value, we have 6 meters, and we have value of 4 meters. Okay, so now let's draw the tributary areas. Okay, so we defined that the tributary area is something like the halfway to the adjacent member. Okay, so another way, I mean, there is still another method for computing the loadings on the columns. So the other one is in terms of the support reactions. So since this is a beam, the slab, I mean the loadings of the slab is transferred to the beam, and then this beam, the reactions of that will be transferred to the column. So if you try to draw it here, it's something like this. So this is your beam, for example. Let's say your girder, or okay, beam, whatever. Okay, so we have this. Since you have these loadings, recall that if you're trying to draw it, this beam dash 1, then we have a trapezoidal loads, or if you simplify it, rectangular load, that doesn't matter. So you have a support, right? So if you have a simply supported beams, then you can calculate the support reaction. So this reaction is actually transposed to this. That becomes the loading, the actual loading for these columns. Okay, so one way you can solve for that, but there's another way that's more direct and probably easier. So that's gonna be, I mean, the load is coming from the slabs. Okay, so this is our column. So let's label C-1, C-2, C-3, C-4, C-5. Okay, so now let's compute the loadings of C-1. Okay, so halfway, so what's the halfway? That's 3 meters. Okay, so let's just do it like that. And what's the halfway of C1 and C-3? That's 4 meters. Okay, so let's try to intersect this. Okay, so meaning this is the tributary area. Now for C-3 and C-4, then you just find the halfway. So this 2.8 plus 2.2, that's 5 meters divided by 2, and that's gonna be 2.5, right? So that's it. So if you notice that interior columns are actually carrying much or twice the loads. I mean, if that's going to be symmetrical, but or that has been the case. But here you'll see that interior columns carries much weight than exterior ones. Okay, so for C-4 this is it, and then for C-5 then it's just find the halfway here, something like that. Okay, so this is more direct because once you have the tributary area, right, actual loadings, recall that for actual loads we have actually unit of kilonewton. So but what we're given is actually the dead load and live loads. They're actually given in kilonewton per meter squared. So what you need is the value of area. So this is it, the area. So the meter squared, the tributary area. So if you multiply that, then you get the value of kilonewton. So B dash U, that's gonna be kilonewton. Okay, so let's solve the column 1. Okay, and the rest I'll leave that up to you, but it's just something like that. Okay, so 6 divided by 2, that's 3 meters, and then this one we have 2 meters. So meaning the tributary area is equal to 3 times 2 is equal to 6 meter squared. Now what's our dead load? Or we can compute for the factor of this. So 1.2 dead plus 1.6 live is just 6.16 from the earlier values that we had. So 6.16 times 6, and that's 36.96, 6 kilonewton, right? So this is the value, the amount of factor loads that's gonna carry by this column. Of course, this doesn't include the column weight. So that's another computation. So you have to include if there's given, since you have the volume, then you can compute for the dead load of this weight of this column. Okay, so since I've said that this is this is just one method, another method is by the reactions of beams and girders, then not supposedly, I think the answer would be the same whichever method. Okay, so let's try to solve the reactions of this B-1 and then this B-5. So we have B-1, let's find this, and then we have B-5. And now let's compare that value to this value. Okay, so checking other methods or other method. Okay, so from B-1, what we get is 105, 10.5 WL all over 2 times the distance or the length, which is 6, divided by 2. We get a value of 31.5 kilonewton. And for B-5, the value is 8.19 times, okay, what is this length? That's 4. So WL over 2, 4 divided by 2 is equal to 16.38. So if we add this up, what we get is 47.88. So what's the problem with this? Okay, so supposedly they must be the same. Okay, so the problem is with regard to the simplifications that we did. Okay, so let's check what if we'll do the actual beam and loading scenario. Okay, so for the beam-5, we have these loadings. Okay, so let's assume a simply supported. And we have a length of 4 meters, and our loadings is like this. Okay, so the actual value of this is, okay, this is it. We are referring to this beam-5. So we have this triangular area. So the location of this maximum point is just simply the midpoint. So that's 2 meters from this point. So 2 meters. Then since this is a 45 degrees, okay, so since this is a 45 degrees, then the distance here to this point, that's gonna be 2 meters. Okay, so that's 2 meters. So therefore, if we try to consider this something like a tributary width, it's not actually a tributary width. We can find this value as 6.16. Okay, so that maximum value right there is 6.16 times 2. So 6.16 times 2, that's 12.32. That's not yet the beam. That's just the maximum load at that point. Okay, so let's say the loads. Okay, so if you try to solve for the support reactions, now let's not simplify it. Let's not make it a rectangular. Okay, so if you try to solve this, and of course using the appropriate equations for the shear under these beam conditions and loading conditions, then what you get is a support reaction having a value of 12.30 kilonewtons. Okay, so for beam-1, we have a trapezoidal loading, so our length is 6 meters. Okay, so again, the tributary width, although it's not really the tributary, the distance from this let's say from this beam-1 to this point, that's just actually the L over X. I mean LX divided by 2, which is just 2 meters, right? So again, it's gonna be 2 meters, and if we multiply the 6.16, what we get is a 12.32 as well. But since we have different lengths and different loadings, then we'll get a different reactions. Okay, so the reactions here, so these reactions is that. So the reactions for this is okay, 24.6 kilonewtons. Okay, so that's the value. Now if you add that, the total that's gonna be 36.92. 92. Okay, so we'll try to draw it here lastly, just to show at least a visual or a visual representation of this type of loadings. Okay, so we have these reactions. We have loadings from beam-5, which is 12.32 kilonewton, and we have another loadings from this beam-1, which is 24.6 kilonewtons. So if you total that, that's 36.92. Okay, so this is not a value from the slab. I mean, from the other method that we use, the area, slab areas. What we get is 36.96, and then this 36.92, so it's just slightly off this decimal decimal value only. So that's gonna be due to, let's say, rounding off or something. Alright, so I'll leave this up to you. The remaining columns C2 to C-5, then you can try solving that, and then so that you can practice out. So lastly, of course, you can always tabulate the results if you want a clear presentation of your output. And I would require this. Say, remember, C-1 was the dead load, it's the live load, it's the factored loads. Of course, it's going to be governing factored loads. And then that's the actual loadings. Alright, so I guess I need to have I guess I need to do another video, last video, just a short video on this topic, and then after that we'll move on to the topic on reinforced concrete. Okay, see you in the next video.